Hi, this is Aaron Jerome, and I'm trying to, mix a video, make a new video. This is going to be part one of my series. Let's see if I can make it work. My series on Introduction to Analog Electronics, Part 1, History of Electronics. This is a picture of Albert Einstein. I love quotes from various places. There's a quote from Albert Einstein that comes to mind that has nothing to do with what we're talking about. But once, allegedly, Albert Einstein was asked, "How does it feel to be the smartest man in the world?" And Albert Einstein responded, "I don't know. You'll have to ask Nikola Tesla." That has nothing to do with what we're talking about, but he did have another quote that does have to do with what we're talking about, and that quote from Albert Einstein is, "If you can't explain it simply, then you don't understand it well enough." This is my main objective as a teacher, and I'm passionate about taking hard-to-understand concepts and making them easier for learners to understand. So, ask yourself, how well do I understand electricity, and how well would I like to understand electricity? Here's what I'm going to start discussing in this video. We'll save some of it for the next video, but in this video we're going to discuss, how did humans first come to understand electricity? How does electricity work at the atomic level? How are magnetism and electricity related? What is an atomic valence shell? What makes electricity flow is probably a topic we'll work on next time, as well as what is a coulomb, what is an amp, how do we measure electricity, and what is a volt. These are things we're going to be working on. If you're one of my students watching this, remember, generally the red text, not this red text, but if you see red text, that is a summary of your textbook. You should write it down. It's really important. Remember, the biggest lie students tell themselves is that they will remember it. I'm saying if you do write it down, you'll probably remember it better. I know I do. Anyway, moving on. So we're going to be talking about what is electricity and how was it discovered. Before we start with that, I need to show you a fish. This is a fish. This is an electric fish. Ancient Egyptian texts dating from 2750 BCE, and if you're doing the math, that's almost 5,000 years ago. They referred to these fish as Thunderer of the Nile. And because they were superstitious or maybe mythical, patients with ailments such as gout and headache were directed to touch electric fish in the hope that the powerful jolt might cure them. An electric fish. If you swim in the Nile and don't get eaten by a crocodile, maybe you could get shocked by an electric fish. But the point here being is that evidence of a knowledge of electricity was recorded, probably known for much longer than that, but recorded as far back as we know, about 5,000 years ago. That was quite a while ago. All right, something else. I'm going to show you another video now. This video, I think, speaks for itself. So hopefully there's no narration, but I'll talk about it afterwards. And hopefully the sound comes through, because the sound is really cool. Okay, so what kind of black magic have we been watching? Well, The way I heard it is thousands and thousands of years ago, sheep farmers, shepherds, they found amber. They found that if they rubbed their amber against a sheep, then it could pick up bits of leaves. That's what's going on in this video as well. People, evidently, they're recreating that amber was found, rubbing amber. Actually, how does that work? Well, what happens is the amber, when it's rubbed against any kind of fur or wool, the amber is charged with electrons. And so electrons have a magnetic effect. They're negatively charged. And so the electrons that go into the amber, well, like charges repel and opposites attract, right? Well, in the amber, there is an abundance of electrons, so an abundance of negative charge, and the neutral charge now is attracted. The bits of leaves, the fur, or the hair are now attracted because the positive charge and the negative charge, it's not a neutral charge anymore because of the abundance of electrons in the amber. So that's why it picks up the hair. It is definitely a magnetic effect, because magnetism is simply the charge of the electrons and being attracted to the charge of the protons, and so that's what has happened. Okay, so ancient Greeks used this word to describe something, and this word is not Nietkpav, and it's not Russian. It's evidently Greek, ancient Greeks. This word has a meaning. The meaning of this word is amber, but the pronunciation of this word, which means amber, is electron. The electron, or the word electron, was first introduced in the late 19th century to describe one of the fundamental subatomic particles that make up atoms. Again, it's a negatively charged subatomic particle, and its discovery marked a significant milestone in the understanding of atomic structure and electricity. The discovery of the electron is accredited to this guy, J.J. Thomson. He was a British physicist in 1897, and he conducted experiments with cathode ray tubes, that's what's in the background there, and found that they emitted a stream of negatively charged particles, which he first called corpuscles. Later, he proposed the name electron to refer to these particles, and the name stuck. I just want to say something about that. This is a glass tube where the air has been evacuated out. Then electricity is brought into this and fed onto a plate at the opposite end, probably a phosphorus plate that would light up. And because it would light up when this left end was energized, something was going on in the middle. And J.J. Thomson said, that's got to be a flow of something, and called it a flow of electrons. But he, J.J. Thomson, was probably influenced by another scientist. I'm trying to remember the name of that other scientist. William Gilbert. He was influenced by the work of William Gilbert, who studied and wrote about how static attraction and magnetism seem to be kind of the same thing. He described this phenomenon using the Neo-Latin word electricus, which meant at the time of amber, or like amber. He was explaining that magnetism was a little bit like amber that could pick up hair or bits of leaves and so forth. So that is from the Greek word for amber, which was electron. J.J. Thomson, over on the right side, he formalized the particle by naming it an electron. From this we got the words electron, electric, and electricity. Back in the 1700s, 1600s, electricity became popular, not because we understood what it was or what it meant, but it became popular. The story goes that a lot of people they for entertainment, they had people over to the house and they performed what was called parlor tricks. And this guy is going to demonstrate one of those parlor tricks. Now, what he has in his hand, I suspect, is basically mylar strips. You might call it Christmas tree tinsel, but those are mylar strips, and he's going to do a parlor trick with them that I'll explain in just a minute. So this is a parlor trick that you can do at home. What's going on there? Well, he's charged, looked like he used some wool, and he charged that tinsel. And because electrons are all like charges, they repel each other, and that's why the tinsel spread out, because every strand is trying to be as far a distance as it can from every other strand, because electrons repel. Then he charged the plastic rod there, the plastic pipe. It's probably just a piece of PVC sprinkler pipe, but he charged it up, and that's full of electrons and also repels the electrons in the mylar sky starfish looking thing. That's what's going on here. So this is an example of a type of parlor trick that would demonstrate static electricity and be used for entertainment at home parties, 1600s, 1700s, things like that. And these types of parlor tricks were instrumental in making electricity a popular topic. So what is electricity? Here comes the first red words. This is a definition I want you to write in your engineering notebooks, which I also call logbooks. Electricity is the flow of electrons. I'll give you a second to write that down, but not too long, because you can pause the video if you need to. All right, what is an electron? Well, to explain an electron, I'm going to go kind of a different direction. What is this? Well, this happens to be a coin that is produced in the United States of America, and it is called the Buffalo Gold coin, which is kind of confusing because that's not a buffalo on the front of the coin. It's called a buffalo coin because on the back of the coin is a buffalo, an American bison, which we call a buffalo. It's about as heavy as about 5.5 quarters. It has a face value on it. If you see that, the face value of this coin is $50. But I'm willing to pay you $100 for each one you want to supply to me. You could make a ton of money, except that the actual value is much higher than the face value, so you couldn't even buy them for $50 because this is a pure fine gold coin, and the actual value as of June 15th, 2023 is about $2,229.37. So, Buffalo coin. On the other hand, I'm just putting a quarter on there at the same scale so you can see roughly, comparatively, how big the Buffalo coin is. This is a Washington quarter coin. Its face value is 25 cents, and its actual value is also 25 cents as of June 15th, 2023. When we weigh gold, we usually use something called troy ounces, and so the weight of this coin is 1 troy ounce. By comparison, the weight of the quarter is about 1/5 to 1/6 as much, 0.1823 troy ounces. If we want to weigh the mass of this coin, we would weigh it. It would weigh in at 31.1035 grams. The quarter, which is roughly the same size, would be 5 or 6 times less the mass of the gold coin, 5.67 grams. The quarter is made of copper and a copper-nickel mixture, and of course the gold Buffalo coin is made of, well, really, really pure gold. So why am I talking about this? Well, I want to talk about how many atoms it takes to make one gold coin. How many atoms, how many individual atoms is in this? Don't ask me how I know. Probably a scientist stared at a wall and figured it out. That's how they always do. Or maybe they use the scientific method and experiments and so forth. We should look that up someday. In any case, there are 97, 889, 187, 817, 258, 883, 248, 731 individual gold atoms in this. Now, if you're in my class, you have already been taught how to convert numbers like this into something that we call engineering prefix or scientific notation, powers of 10 notation. So if you know this, you already know that you can convert this number into 97.889 times 10 to the 21st power gold atoms. Maybe that still doesn't register. If it doesn't, well, it's bigger than 1,000, bigger than a million, bigger than a billion, bigger than a trillion, bigger than a quadrillion, bigger than a, what, pentillion? Let's see. 1,000, million, billion, trillion, quadrillion, pentillion, sextillion. 97, about 97 sextillion gold atoms. That is a lot. What I'd like to do is kind of zoom down into a single atom and talk about that for just a minute. So here we go, down to a single atom. Okay, it's not really a gold atom, but pretend that it is. If this were a single atom of gold, dividing it any further would mean it's no longer gold anymore. For example, gold must have 79 protons to be gold. There's gold right there. The atomic number is 79 and the symbol is Au. So it has 79 atoms in it. And cutting this nucleus in half would mean it's a completely different atom. If we cut it in half, it would then, one half would be yttrium and the other half would be zirconium. And, well, alternatively, removing a single proton would mean that we have a hydrogen and a platinum atom. So adding a single proton would result in mercury, and of course, changing any protons at all would result in kaboom, or what's known as fission or fusion, which can release huge amounts of energy, which explains why we can't successfully make our own gold. So, how does gold get made if we can't make gold because of kaboom? Well, gold and all the heavier elements are made when a star explodes, and it's called a supernova, and it looks like this. Kinda. And the reason I bring that up is because it's very likely, I don't know how likely it is, but we're seeing it in the news a lot right now at the making of this video, that one of the stars in the constellation of Betelgeuse is about to go supernova. Let's learn a little bit more about that.
Betelgeuse is a red star only 600 light years from us and forms the left shoulder of the Orion constellation. It's absolutely gigantic, 600 times the size of our Sun, easily capable of swallowing the inner planets if it was in our solar system. Betelgeuse is due to go supernova any day now, and there's even a chance it already has. Because it's 600 light years away, it'll take that amount of time for the explosion to reach us, and when it does reach us, it'll be as bright as the moon, bright enough to cast shadows at night. The Earth's atmosphere will absorb most of the high-energy gamma rays generated by the explosion, allowing only a small fraction to reach the surface. At 600 light years away, this still isn't close enough to pose a severe risk for life on Earth. For that, we need to get even closer, somewhere in the region of 30 light years away.
Okay, so just a quick review. This star, Betelgeuse, about 600 light years away. I've seen other sites say 724 light years away. It's been going dimmer and brighter, so we've had our eye on it because we know it could go supernova. Anytime between right now and 100,000 years from now, but it's in the news because it dimmed dramatically in 2019. It's doing something different. Of course, if it is, it probably already went supernova, could be 600 light years ago, but we don't see it until the light reaches us. So when we see it, it's expected to be nearly as bright as the moon. We'll be able to see it in the daytime. Diameter of Betelgeuse is about 700 of our suns, and the first sign that it has exploded will be a shower of neutrinos will reach us. Those are gravity waves, and we won't be able to see them, but scientists will be able to use their fancy gadgets to detect the surge of neutrinos, and then it'll be all over the news, and there probably won't be anything else on the news. And so, like I said, could happen tomorrow. When the light arrives, it will be super bright for evidently about a year, and then after that, still be visible as one of the brightest stars in the sky, even without a telescope, for many years, probably for the rest of our lifetime. To me, that is really interesting. I hope this thing goes supernova in our lifetime. By the way, the explosion of supernovas, that's where gold comes from, and all of the other elements really that are heavier than helium. The sun can fuse hydrogen and helium, and that's where the energy comes from that we get here on the Earth from all the photons getting to the Earth, and we use them for energy. So I guess it's also true that if everything else came from all the other elements came from the explosion of the supernova, that's why they say that we are made of stardust. Kind of an interesting idea. Anyway, back to this atom. Let's talk about things we already know. Just reviewing, this is the nucleus of the atom. It is contained of protons, positive charges, and neutrons that have no charge. Orbiting this nucleus of an atom are the electrons. They're orbiting like a fruit fly orbits around a peach. Electrons are, I'm going to stop them so you can see them. Electrons are negatively charged particle. What does charge mean? What does it mean to have charge? Well, when we say charge, we mean the strength of the magnetism. We also mean how many electrons compared to how many protons, and that is the strength of the magnitude. What is charge? Some of this is red text. You'll want to write it down in your logbook. What is charge? Have you ever heard the quote, like charges repel and opposites attract? That's something you need to write down in your logbook, your engineer's notebook. Electrons are negatively charged. That means they are like charges, and like charges repel. Oops, there they go. They're repelling each other. Protons, what do you think they do? Well, they're both positively charged. That means they're both like charges, the same charges. That means protons also repel protons. Look at all those red words. You need to make sure you get them in your engineer's notebook. Oops, there it goes. The protons have also repelled each other. Now, if you need to, you can stop the video to get these red words, but I'm moving on. They don't seem to like each other. At a party, they would stay on opposite sides of the room. But on the other side of the coin, I guess there was a pun there, its opposites attract. Protons and electrons have opposite charges. That's also a red word, so make sure you get those down. They are attracted to each other, like a magnet. In fact, the attraction is magnetism. It should be noted here probably that protons are about 2,000 times larger than an electron. Well, they're actually closer to 1835 times larger than an electron, but you know who's keeping track. Back to the atom. Okay, note, this is just one kind of model of the atom. It helps us to understand the atom. The electrons are orbiting the nucleus, the protons and the neutrons, and each electron seems to have its own orbit. That's almost true. In reality, the electrons would orbit so fast that they would seem to be everywhere at once. We're slowing them down in this model. But each orbital, the electrons are so fast, and maybe you've heard, you cannot know the position and the speed of an electron simultaneously. These things are going super fast. So the electrons would go so fast that it would look like they're everywhere at once, and so the orbital would probably look more like the shell of an egg. We wouldn't be able to see through the multiple orbital shells then. In another atomic model, we might flatten the orbits out to better understand them. I believe this model of the atom, there's probably 20 models of the atom. They're all wrong because we don't yet have a single model of the atom that is accurate. But this model, I think, is named the Bohr model, as in Niels Bohr. Valence electrons. We need to talk about the valence electrons. There are many different models. I talked about that already. None is perfectly accurate. The outermost orbital is called the valence shell. You need to have a definition of what the valence shell of an atom is. The outermost orbital is called the valence shell. That is really important to us because the valence shell is what facilitates electricity. The rest of the orbits are important too for chemistry and physics and even for us, but this outermost valence shell is really important to the field of electricity and electronics. How many electrons are in the outermost shell? Well, 2, 4, 6, 8. There's 8 of them. There can never be more than 8 electrons in a valence shell. We'll probably explain more about that because there are further out shells and more electrons in this shell, but if it's the outermost shell, no more than 8. What that tells me is that whatever atom this is, it is an insulator atom. Talk more about that later as well. 8 electrons means it's an insulator. Now, I put a new orbital or a new valence shell on the outside. This one only has 2 electrons, and by looking at this one, I know right away that this is not an insulator, but a conductor atom. It has to do with how many electrons are in the outermost shell. This one only has 2 electrons. Sometimes valence shells can escape, sometimes valence electrons can escape the valence shell, but only if there are fewer than 5 electrons. More than 5 or more cannot escape. Exactly 4 are what we call a semiconductor, and we will talk more about that in later discussions. So sometimes the valence electrons can escape. Only valence shell electrons can escape. The rest are locked in, but when electrons escape, they move to a different atom. Make sure you pause this video and get all of these red words in. You'll need to review them for tests and so forth. Okay, so this is a group of atom, and we're only looking at the valence shell, and we're noticing that electrons are jumping from one valence shell to another. And if electrons are jumping from one valence shell to another, it means the flow of it's a flow of electrons, and therefore it is electricity. Since electrons moving can do a little bit of work, let me explain that a little bit. An electron is a package of, it's charged with photons, but it is a negatively charged particle, which means we can use the magnetism in that particle to push or pull other magnets. And for that reason, a single moving electron can do a little bit of work. 2 electrons can do twice the work. But when we use electrons to do work, we use trillions, quadrillions, or quintillions of electrons that flow, and that can do a lot of work. A quintillion electrons can really do a lot of work. But what work can electrons do? Let's go back to thinking about electrons like water, like we did in the earlier video presentation I did before. Check the other videos that I have published. And let's talk about water for a minute and compare that as a similarity to electrons. This is a water motor. Gravity pulls the water down, the falling water turns the wheel. If the drops of water were electrons or negative, and if the paddles of the wheel were magnets, also negative, then the electrons that are falling down the stream of electrons would push those magnets out of the way and cause the wheel to turn, and then we would have an electric motor. To do this, we need to be able to turn the magnetism on and off, or turn the water on and off. But this is a magnetic motor. Incidentally, it could also be a generator. We'll talk about that later on. But you can see let's call the red negative and the blue positive. So if the blue is positive, it's pulling the red. But when the red gets over here, it pushes the red because like charges repel and opposites attract. Same down here on the bottom. But to keep this thing from stopping, becoming balanced, we actually need to be able to turn the magnets on the top and the bottom on and off, and we can do that with magnetic coils, and that is the basis for an electric motor. How do we measure how much water is falling on a water wheel? The intensity of the current increases when more water flows, and that causes the wheel to turn faster. More work can be done if we add more water. Same thing with an electric motor. More work can be done if we add more electrons. But how do we measure the intensity of the water's current? Well, to measure the current of a stream of water, we count how many gallons of water, and each of these blue dots is meant to represent a gallon of water. How many gallons flow past a specific point in 1 minute? So we count and we measure, and we might describe this flow as 18 gallons per minute. 18 GPM. That is how we know, that's how we quantify how much work water can do. Well, an amp, or doing work, an amp, I'll get back to amps. Doing work with electrons is kind of the same thing. So to make a wheel go faster, we increase the GPM, the gallons per minute, and to go slower, we decrease the GPM. And it's kind of similar to electrons. To measure the current of electrons, we need to count how many electrons flow past a point, but we do it in 1 second. Couple of problems with this that you probably have already thought of. Keep in mind, if you haven't thought of it, that electrons are super tiny and they move super fast. So the poor guy that has to count electrons can find them very hard to count, and there must be a better way to count electrons. Well, what we need is a really smart guy that can figure this out, and this is the guy. This guy found a better way to measure charge, which is another way of saying counting electrons. Right? His name was Charles Augustin de Coulomb. He was a French physicist of the 1700s. So he did this a long time ago. He discovered what is now called Coulomb's law, which we don't need to really get into in much detail, except that you've probably already come across Coulomb's law, which is very similar to the law of gravitational attraction. Gravitational attraction, if you're familiar with it, you don't need to know it for this class, but basically you take two objects, like two planets or a rock and the Earth, and you multiply their mass. And then you divide that by the square root of the distance between them, and then multiply that by a special secret number called the gravitational constant, and you have a description of the force of gravity. Well, Coulomb's law is very similar to that. Coulomb's law, though, uses charges. So maybe we have a big charge here and a little charge here. We simply multiply those two charges together. You have to have two charges for there to be magnetism. You have to have two objects for there to be magnetism. And then you measure the distance between those charges, multiply that, square that distance, multiply that by Coulomb's constant, which is K, secret mysterious number that makes it all work, and that equals the force of magnetism. Again, you don't need to know this, at least not early in this course, but it's nice to know at least that much for now. Okay, so to discover his law, Coulomb needed to invent a new measuring tool, which is what he has with him here in the picture or in the painting. He designed this device and he called it a torsion balance. This is kind of cool. I wish we had time to make a torsion balance, because this is how it was done originally. Here's how a torsion balance works. This device has a thin vertical wire, which I will represent with a red wire, or a red line. That is a thin vertical wire. And then he suspended a needle at the bottom. We attach that to the wire. Pardon me. At the end of the needle was a foam ball. I actually am going to build one of these. I've ordered off of Amazon some small metallic spheres about 1 inch in diameter. So I'm going to call these metallic spheres. Okay, there's one there. It's resting against a second metallic sphere, and they have the same charge, so there is no repelling going on here. At the other end of the needle is just an angle indicator, and then there is a protractor that's wrapped around, and so we can use this device to measure how much repulsion there is between the two metallic spheres. So then notice the metallic sphere on the bottom on the left actually is attached to the top of the container, and some of these torsion balances simply have the little sphere on the left attached to a metal rod that goes outside. Then you can inject electrons from the outside. What they're doing here, though, is injecting electrons by using a third metallic sphere that has been previously charged with an overabundance of electrons, giving it an extreme negative charge. So what they do is they lower that down into the apparatus, and the electrons jump from the upper metallic sphere, and it jumps down into the other spheres. And since the two spheres are full of electrons now, they repel each other. And you can measure the distance they repel by measuring the angle on the other side. And this is what Coulomb did. He did some other fancy footwork, but eventually realized the ratios involved to derive the equation for electric charge, Coulomb's law. So this apparatus actually allowed us to know how many electrons are in a group. And just like in the international system, metric, there are standard values, like there is a standard length of a meter and a standard volume of liters, and just like that, there is a standard charge. So the standard SI system metric has defined a standard charge for a group of electrons, and this standardized group of electrons has, and you really should write this, well, don't write this number down. We'll convert it to engineering prefix notation. But it has a lot of electrons. That way, you don't have to count each one. It has more than 1,000, more than 1,000,000, more than 1,000,000,000, more than 1,000,000,000,000, more than 1,000,000,000,000. It is actually 6.24 pentillion electrons. Also 6.24 times 10 to the 18. 6.24 quintillion. Is that right? Or is it pentillion? Let's do it again. 1,000, million, billion, quadrillion, pentillion. Let's do it again. 1,000, million, billion, trillion, quadrillion, pentillion. I've got this wrong. It's not quintillion. It's pentillion. 6.24 pentillion electrons. In 1881, this standard amount of electrons was named the coulomb in honor of Charles Coulomb. So now that we have a standard unit of electrons, we can count those instead of counting individual electrons. It's just a lot easier. So we would count how many coulombs flow past a point instead of individual electrons in 1 second. And when we do this, this is the definition of an amp. So these are red words, the definition of an amp. Here's an equation. I want you to write this down. 1 amp is equal to 1 coulomb per 1 second. If you're standing here counting and you count a whole coulomb of electrons that pass by in 1 second, you have just identified an amp. What's an amp? Well, it's a really fast flow of electrons. And if you didn't understand that before, now you know what an amp is. Think about it. You understand what an amp is, and I think that's cool. You know, like Einstein said, if you can't explain it simply, you don't understand it well enough. So if we're going to explain what amps are, well, the simple explanation is it's just a whole bunch of electrons flowing really fast. But if you want to be a little more formal, you can say it is groups of electrons that are called coulombs. If 1 coulomb passes by one point in 1 second, that's an amp. Today, we can measure amps on sophisticated devices called multimeters. We can also measure volts and ohms and a few other things. But in 1881, this measurement, the flow of electrons, was named amperes in honor of André Ampere. And André Marie Ampere, he is famous for his discovery of that and a few other things, specifically that electricity and magnetism always occur together. If electrons are flowing through a wire, then magnetism is flowing around the wire, right? And so this can be explained by the right hand rule. If you grip a wire with your right hand, with your thumb pointing the direction of the electron flow, then your curled fingers indicate the direction of magnetism that is in the wire. That's what the right hand rule is. In fact, what this means is that electrons and magnetism are always present together, meaning what we're talking about is not just electricity, it's electromagnetism, which really can't be separated. You may have heard that space-time can't be separated, and it illustrates the constancy of the speed of light. Well, this is like that. Magnetism and electricity cannot be separated. Okay, so I'm going to show you a quick video that shows the forces that are flowing through through wires, showing you that if the electrons are both flowing the same direction, they're going to repel, and if they're flowing opposite directions, they're going to attract. So all we're doing is hooking up a car battery to some wires, and when we make them flow one direction, they repel. When we make them flow the same direction, they attract. Here's just a close-up version of that. We're calling it series because the electrons are parallel, because they're flowing. Parallel means, well, they're going too fast. Series means they're flowing in the same direction, which means they repel. Parallel means they're flowing in opposite, or something like that. I'm going to have to think that over and get back with you on that. Anyway, another thing I wish we had time to do in our class, but maybe I'm thinking it'd be nice if I could do just an analog electronics class and slow down, and then students, you would build all of these little gadgets that were invented to discover properties of electronics all those hundreds of years ago. Back to the water wheel. To make this wheel go faster, we would increase the gallons per minute, right? To go slower, we would decrease the gallons per minute. To make a motor go faster, it's the same idea, but we use different words. To make a motor go faster, we increase the amps. To make it go slower, we decrease the amps. Remember, amps are just a flow of electrons. Okay? So, this is the end of this video. We're going to be talking about other things, the other topics that we talked about at the beginning of this video in the next video. So I hope you enjoyed this. Thanks for watching. Please come back to Jerome Electronics. And if you want to tell me what's wrong with my video, you can actually email me at jeromeelectronics@gmail.com. Thank you. See you in the next video.